Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And with this in mind, this video is going to focus on Unit 4 with the WJEC Chemistry, which is the organic chemistry, and we're going to be working through some past paper questions, mainly linked to the carboxylic acid topic, but it does cover a bit of aldehydes, ketones and alcohols. So if you find this video helpful, please remember to like, subscribe, share with your friends and keep checking back for more content. Okay, so in this question here, you've got a benzene ring with a methyl group. That is your starting point. That's methylbenzene, sometimes called toluene. And in the first step, you are converting the methyl group to a carboxylic acid. And I always like to highlight the bit of the molecule that's changing. You're going from a methylbenzene to a benzene with a carboxylic acid group. That's the only bit that's changing. To do this conversion, you need to use the reagent potassium permanganate, so KMNO4, but because it asks for the name of it, it would be alkaline potassium permanganate. And then it asks what is reagent S, which follows on from that. Well, the key thing is, because this is under alkaline conditions, you actually end up with the salt of the carboxylic acid rather than the carboxylic acid itself, so you'd need to acidify that, so we'd use something like hydrochloric acid. So let's reflux it with alkaline potassium permanganate, normally in aqueous conditions, a bit of water, and then you acidify to turn the methyl group into the carboxylic acid. And then reagent T is going to convert the carboxylic acid into an alcohol. So reagent T must be a reducing agent capable of reducing a carboxylic acid, so that's lithium aluminium hydride. Don't be tempted to go for sodium borohydride because that's not powerful enough. So lithium aluminium hydride. And then this alcohol here is reacted with HBr, and effectively what happens is the OH group that's here substitutes for the bromine, and you end up with this molecule here. So you've got a benzene ring, you've still got your CH2 group, but rather than an OH group, you've got a bromine. Okay, in this question here, you've got this rather strange looking molecule reacting with reagent A to form this molecule, 3-oxobutanoic acid, and the reverse of this reaction involves sodium borohydride. Now, sodium borohydride is for reducing, so the opposite of reducing is oxidation. So reagent A must be able to oxidize this molecule here. So it's worth looking at the structure and seeing that this is an alcohol group. So you've effectively got a secondary alcohol. And that is being converted into a ketone group. So to oxidize a secondary alcohol into a ketone, you need acidified potassium dichromate. So acidified potassium dichromate. And then it says both 3-hydroxybutanoic acid and 3-oxobutanoic acid will undergo the triiodomethane reaction, which is sometimes called the iodoform reaction, sometimes it's called the haloform reaction. State the reagent used for this reaction and the observations made. So you need two reagents for this reaction. It's the test for a methyl ketone, or something that can be oxidized to a methyl ketone. So you'd need sodium hydroxide and iodine as your two reagents. And the observation is a yellow precipitate. The next question wants you to show that you can do curly arrows to represent nucleophilic substitution for an unfamiliar molecule. So you've got 2-bromo ethane here, or bromoethane, and then you've got this OCH2CH3, but the key point is this oxygen here has a negative charge on it, so it's going to act as a nucleophile. So this is your nucleophile here. Because it's negatively charged, it's attracted to something positive. We next need to recognise that the carbon to bromine bond is polar, so the bromine would be delta minus and the carbon would be delta plus. That's just purely based on the difference in electronegativity, bromine being more electronegative than carbon, and therefore these are what we call partial charges. They're sort of showing the difference in electronegativity. And then our nucleophile, or more specifically the oxygen within the nucleophile, is attracted to this delta positive carbon. So we have a curly arrow that is going from the oxygen to the carbon. And then this carbon here is now making too many bonds, so this carbon to bromine bond breaks. So you have your curly arrow going from the bond onto the bromine. So you've got a bond making curly arrow, making a new bond between the oxygen and the carbon, and then the carbon to bromine bond is breaking. The question doesn't ask for it, but it's worth drawing out what the product would look like. You'd have the 2 carbons that are here already, you've lost the bromine, and you've now got a new bond to oxygen, and then a new bond to carbon, and then another bond to carbon. So you'd have CH3, CH2O, CH2, CH3. And this molecule here is called an ether. It's a type of functional group. You don't specifically need to know it for A-level chemistry. It's not on the WJEC specification, but it's where you have this oxygen bridge between alkyl chains. Okay, so this question here is a synthesis question, where you start off with the molecule that I'm going to shade into orange. It's always worth just looking at the molecule. I recognise this might be a bit small, especially if you're looking at it on a phone. Probably better to look at this on a laptop rather than a phone. I can't get the whole thing any clearer than this. But you've got 2 functional groups. You've got an amine on the left-hand side, and you've got a halogenoalkane on the right-hand side. And in the first step, the halogenoalkane, the carbon to chlorine bond, is breaking and substituting with the cyanide group. So to do that, that is nucleophilic substitution, and you would need to use potassium cyanide, KCN. So potassium cyanide, and the cyanide ion substitutes for the chlorine. If you want to look up the mechanism for that, there's a video on here on nucleophilic substitution. The question doesn't actually ask for it here, though. It's just wanting the reagent at this stage. Reagent N is then converting the nitrile group, this bit here, into an amine. To do that, you need to use lithium aluminium hydride. That needs to be anhydrous. Absolutely no water there. That's for reagent N. For reagent K, the key thing is that you're changing your amine into an amide. And the easiest way to do that is to react it with an acid chloride. Now notice that you've got 2 carbons added on to the structure, so it must be an acid chloride with 2 carbons, so it will be ethanoyl chloride. So ethanoyl chloride. And just to show you the structure of that, that's C to C, double bond to O to Cl, and then CH3 there. Yeah, and for the last one, you're hydrolyzing the nitrile group. You could do that under acidic conditions. However, the only problem if you do that under acidic conditions, I'm just looking at, is that your amine group might interact with the acid. So maybe aqueous conditions would be better for that one. If you did it under aqueous conditions, you'd reflux it with aqueous sodium hydroxide and then acidify. And then acidify. Okay, so this question here is all about this molecule called guaiacol, which is not a molecule you're probably familiar with, but if you look very carefully at it, you've got a benzene ring bonded to an OH group, so it's a phenol. And then you've got this OCH3, which is an example of that ether functional group I mentioned earlier. And it says that guaiacol reacts with aqueous bromine, and it does so by analogy with the reaction of phenol with aqueous bromine. So that's one that you need to know from your phenol topic. So if we just take phenol a second, if we take a phenol, it's a benzene ring with an OH group. Let's just remind ourselves of the reaction. If you react it with bromine, because phenol is more reactive than benzene, because of the oxygen donating its electrons into the pi cloud, it will react with bromine via the electrophilic substitution without the need for a catalyst. And what happens is you've still got your phenol group, but you substitute in the 2, the 4, and the 6 position to give 2,4,6-tribromophenol. And the byproducts would be 3 lots of HBr, and therefore you need 3 lots of bromine. Now it tells you that guaiacol reacts in analogy to that reaction. It's analogous. However, the only difference is this is the 2 position, and it's already blocked with something else. So you can get exactly the same thing, except for this OCH3 will stay in the 2 position. So to draw out the product, you'd have your benzene ring with the phenol group. You'd still have your OCH3 in the 2 position, and then the bromine in the 4 and the 6. So that's the only acceptable answer there. In terms of what is seen, when it asks a question like that, is what are the actual observations? If you did this reaction in the lab, what would you see? 2 things. You'd see the decolorization of the bromine water. So the aqueous bromine would go from a sort of orangey brown to colourless. So let's just say orange to colourless. But also you'd see a white precipitate, which is the formation of this bromo compound. You need both the observations for the mark there. The next question is about a percentage yield. It's a percentage yield calculation. So what you've got is you've got ethanol, which I'll shade in orange, and it's being converted into this ether molecule, which I've shaded in green, called epoxyethane. So epoxyethane is the molecule in green, and ethanol is the molecule in orange. And what she did is she used 69 grams of ethanol, and she ended up with a 45% yield of epoxyethane, and you're also given the molecular masses. And what you're asked to do is to calculate the mass of the epoxyethane that she obtained. So what you do is you start off by working out the moles of ethanol. That's where I would start. And moles is mass divided by molecular mass. So that's the 69 grams of the ethanol divided by its molecular mass, which is 46. And that gives you 1.5 moles. The next thing to do is to work out the moles of the ethoxyethane, the thing in green. Notice the ratio here. You've got 2 moles of ethanol producing, well, there's effectively a 1 there, there's an invisible 1. So it's a 2-to-1 ratio. So we need to divide by 2, which gives you 0.75 moles of ethoxyethane. We now want to work out the mass of ethoxyethane that could be made, so we times it by its molecular mass, which is 74. And that comes out as 55.5 grams. However, that's not the final answer, because if you look at the question, it says that she only obtained 45% yield. This is what we call the theoretical mass. It's the mass that she could get as a maximum mass, assuming the reaction was perfect with no side reactions, no unreacted starting material, that kind of stuff. So we now need to work out what 45% of this number is. The easiest way to do that is to times it by 0.45. And that gives you an answer of 24.98 grams. However, looking at the level of detail in the question in terms of significant figures, everything's to 2 significant figures, so I'm going to call this 25 grams. Okay, so this question here is all about compound W, and it says compound W can be oxidized to produce benzene 1,4-dioic acid. The reaction can be undertaken in the same way as the oxidation of methylbenzene to form benzene carboxylic acid. So they're trying to jog your memory as to which bit of the notes it is, because it's an unfamiliar reaction slightly, but it's analogous again to a reaction that you do know. So when you look at the structure, it's worth highlighting the different functional groups. You've got a carboxylic acid on the left-hand side, and notice that the carboxylic acid hasn't changed. So that side of the molecule, nothing's happening. You've then got your benzene ring, and then on the right-hand side, you've got this alkyl chain here. And that is the bit that's getting oxidized to form the carboxylic acid. So it's this green section turning into the blue section. And you need to give the reagents and conditions. Well, to oxidize an alkyl side chain on a benzene ring into a carboxylic acid group, you need to reflux with alkaline potassium permanganate, KMnO4, and that needs to be in aqueous conditions, so dissolved in water. However, because it's alkaline, that will give you the salt of the carboxylic acid, so you'd need to do an acidic workup, add a bit of acid when you finish the reaction, so an acidic workup. Not quite sure how they divvied up the 2 marks on that, but you'd need all of that information to get both the marks. And then this question here is quite a tricky one. Well, there's 2 marks available for it. One of the marks is easy, and the other mark is quite hard, I think. So you've got this question about a cyclic ester, which is shown here. So you've got a benzene ring, and then an ester group that is, rather than in a linear chain, it's in a ring. The first thing you have to do is to highlight where the ester group is by putting a circle around it. Hopefully that's relatively straightforward. But then you had to look at what the product would be if you did ester hydrolysis on this. Now, when you hydrolyze an ester, you end up with the carboxylic acid and the alcohol. Although it's done under aqueous conditions, alkaline conditions, so you'd end up with the salt of the carboxylic acid. So what happens in this case is the benzene ring would remain unchanged. So that's nice, you can just draw a benzene ring. You've then got your carboxylic acid in the salt form, so the C double bond O, then the O minus. This bond here is kind of breaking. That is dreadful bonds. Let me draw those again. They're not very straight at all. And you'd form the alcohol. And then this would, the reverse of this is it would cyclize again to form the ester. So basically you've got to imagine what it would be if you broke this bond here. Actually, no, it's more like breaking this bond, really, isn't it, to give you the alcohol. But anyway, that would be the answer. The next question is about atom economy. Atom economy is calculated by the molecular mass, the MR, of the useful product, useful P, divided by the MR of all the products. And then it's times by 100. So the useful product is the phalide P here, which has an MR of 210. To work out the molecular mass of all the products, we don't know what the other products are. However, we know the molecular mass of all the reactants. And because atoms can't be created or destroyed in a chemical reaction, the molecular mass of all the products must equal the molecular mass of all the reactants. So it must be the 310 plus the 28. And then we times this by 100. So yeah, and that comes out at 62% or 62.1% to 3 significant figures. I've gone with 3 significant figures just because the data in the question is all to 3 significant figures. And that's the general rule of thumb. Give your answer to the number of significant figures that the data is given to, and don't round any answers until the very end. And then the last exam question here has 2 compounds, compound Q and compound R, and you need to give a chemical test that would distinguish between the 2 compounds. So it needs to be a test that will give a positive result for one and a negative result for the other. Compound Q has aldehyde functional groups. Compound R is a secondary alcohol. And you've also got iodobenzene. This is a benzene ring, by the way, C6H5. So really, something that will give a positive test for an aldehyde is probably the best route to go with this. So you could go with Tollens. Tollens reagent, that's a pretty good way to go. So Tollens would give a silver mirror for Q. And then no observable reaction for R. Or if you don't have any Tollens to hand, you could use Fehling's reagent. You only have to give one of these answers, by the way. You don't have to give all of them. This is just a bit of revision. Fehling's reagent would give a red-brown precipitate for Q. And no observable reaction for R. It's really important that we write this out, because there's 3 marks available for this, and 1 mark would be for the reagent, and then 1 mark would be for the observation for each compound, so showing you're getting them the right way around. So if you just wrote Tollens, silver mirror, you'd probably only get 1 mark, because you've got to say it's Tollens, silver mirror for Q, and then no observable reaction for R. And if you didn't have any Tollens or any Fehlings, because the aldehyde group contains a carbonyl, you could use 2,4-DNPH as well. 2,4-dinitrophenohydrazine. I believe it's acceptable just to write 2,4-DNPH though for the exam. And that would give a yellow-orange precipitate for Q. And once again, no observable reaction for R. Well, thank you for taking the time to watch this video. I hope it was helpful. If it was, remember to like and subscribe and keep checking back for more content. Thanks everyone, see you next time.